giving the talk. Thank you very much for letting me virtually present. It's good to be virtually there. Sorry to not be able to come. So this is a rather new type of talk for me. I have to say that for our community and for myself in first person is a rather unexplored area. So it feels a little strange to me to come at DIMVA showing such a slide with, this kind of application scenarios. And of course, with Marco and myself wearing hard hats, which apparently have been already used by other speakers. I'm glad was a source of inspiration. So other than that, I would say that this technology is widely used and much more pervasive than I thought when we started this research. It's used in agriculture, it's used in construction, mining industry, logistics, and harbor, for example. So it's used everywhere, and it's one of those technologies that is likely to stay there for a long time because it's a legacy technology. It allows human operators to using these remotes, which are handheld or belly packs, wearable, to control very heavy machinery such as hoists, pumps, cranes, huge tractors, and things like used in marines and stuff like that. So I would like to start off with interesting bits, security findings. In this paper, we perform an extensive security evaluation of this technology, and I would like to start right off with what we found, and then we're going to go into the details of how we got into that point. So in one slide or one sentence, very likely your garage door opener or your car door opener is more secure than this technology, unfortunately, I would say. None of them have any type of rolling codes, so it is possible to record and replay a message. We've tested this in about a dozen facilities, like in the real world, and we found no security mechanisms whatsoever. There's no message encryption or obfuscation, so it is possible to forge commands without needing to pre-record them. It is possible to forge even emergency messages that are used to put the device in full stop. So it is possible to keep the machine in persistent denial of service. It is possible to hijack a pairing sequence, so an attacker can create a full clone of a real transmitter to impersonate the real transmitter. And at the firmware level, there's no code integrity whatsoever, no hardware mechanisms to prevent or to help verifying the integrity of the firmware. So it is possible to Trojanize the firmware on those devices. And all of the vendors that we've inspected are vulnerable to these attacks. So the bottom line is that there is very, very low security awareness in this domain. And that's why I want to start with the second most important part of our work, which is the vulnerability disclosure. It was a hard process. In the end, we have obtained 5 CVEs, and the US ICS CERT released 2 important alerts, which I think is still a good achievement. But I would say that in this domain, it is even harder than in the classic ICS domain, where at least we had some common ground between people working in ICS and people working from IT security. I mean, we had some common background that we could, use to communicate, so to speak. So some of the reactions that we received from the vendors were a bit puzzling because, it seems that some of them did not have security in their radar. So even if some vendors replied right away and say, oh, yes, of course, we're going to patch, then they released a patch, and the patch was version 0.00A, which indicated that probably that was the only and the first software release that they ever did. Other vendors replied that they were not aware of what a vulnerability was, so they wanted more assistance to understand what the problem was. So we had to extend a little bit the disclosure window, and ZDI here was of great help. Other vendors reacted a bit abruptly. They said, maybe we should talk to our legal because maybe we should sue you. And then they kind of pedal back and say, no, wait, maybe we will patch. So again, good result, even if the beginning wasn't very promising. Other vendors simply did not reply. So very mixed reaction. And I think that the root cause is that in this domain, the threat model is on radio attacks is outdated. Some of the arguments that we hear is, oh well, but the attacker has to be close to the target in order to be able to launch this kind of attacks. And I'm like, yeah, close. I mean, 300 meters is the default range of these devices out of the box. So doesn't look very close to me, right? So it's far enough for an attacker to be invisible in my understanding of an attacker. And if the attacker is equipped with proper antennas or power amplifiers, he or she can even be kilometers away. I recall that one of the chips that we found inside the devices that we've analyzed is able to go 100 kilometers in line of sight. Well, maybe you don't always have line of sight, but still it's a very wide range. The other argument that we hear is, oh well, but it takes money and skills to launch these attacks. Only certain attackers will be able to launch them. Well, maybe yes, this could be true. Could have been true for like 5 or 10 years ago when radios were entirely made of hardware, and they would take up a lot of space. They were expensive, and to build them and to customize them, it was a lot of work. So yes, in the past, the attacker would have a very high barrier to entry. But nowadays, radios are almost entirely programmable in software. All the hardware is doing is the capturing and the synthesis of the signal. So all of the difficult part is already taken care of by the hardware. And in software, you can do great things. You can build custom receivers very easily and with very low price. You can even build for $40 or even less if you're good with electronics. I'm not. You can build a local cellular bridge that will allow an attacker to with very small investment to be on the other side of the world while being within the range of the target device. So these things nowadays are possible, and in the past they were not. So I think the vendors will have to revise their attacker model, their threat model. I'm sorry. So how did we get to this point? In addition to the testing on the fields that I briefly mentioned at the beginning, we did a lot of black box analysis, and then I will follow up with a white box analysis later on. But first, I want to start off by explaining how does it work. How do we go about basically doing a security assessment of one of these devices? So we start by treating this as black boxes with antennas that transmit and receive. So the first thing you need to do is to figure out the frequency range. Depending on where these devices are sold, they transmit in certain well-known bands, but the exact frequency is not necessarily known. So you either are lucky and have an FCC entry in the database that will give you access to details, including the frequency, or you use a spectrum analyzer, such as the one that you see on the top right of the screen, and you use a software-defined radio to basically probe what the frequency is. Of course, you have to use the device meanwhile. The second thing you have to do is to figure out the modulation. That is, how the signal, how the the zeros and ones, or how the symbols are modulated into analog characteristics. So for example, is it analog shift, amplitude shift, like it's shown at the topmost right? Or is it frequency shift or phase shift? I mean, there are various options that you have to figure out in order to understand how to demodulate the analog signal. And then you have to figure out what the alphabet is. What are the zeros and the ones? And it's not 100% sure what is the assignment of the symbol, because here with zeros and one is easy, so to speak. But if you have more than two possibilities, it might be tricky to understand to what level of, this is frequency shift in this case, but to what level of deviation the symbol is assigned. So is the second level 0, 0, or is it 0, 1? I mean, it really depends on what the manufacturer decided to do. There's no standard here. And then you have to figure out how long each symbol is in milliseconds, or number of samples, capture samples. And this is very important in order to be able to demodulate correctly and not confuse symbols with each other. Once you have all of these parameters figured out, you can tell that you know everything about the physical layer. So you can go from analog captures with software-defined radio up to a bit stream, right? But you're only halfway through. You don't really know what these devices are talking to each other. So the next step is to figure out the link layer. So you have to be able to see through the bit stream and see where the payloads start and where the addresses are. In this case, we have several ways of addressing, so to speak. In most of the cases, there is a sync word which tells the receiver that the packet is addressed to that specific receiver. The preamble is usually 010101 or 101010, and is used to wake up the receiver, because the receiver usually stays in a sleep mode to save battery or to save energy in general. Then you have to figure out the application layer, which is encapsulated into the payload. Only part of the payload is the actual command. So the actual movement that the operator wants to issue to the connected machine. Great, so I think this is the most difficult part because every vendor does something custom, so it's hard to draw a line and say, oh, here's how you do it, right? Normally, and this is what we followed in our paper, you take many captures. Here's an example of what we did in one of the devices. You take many captures of payloads under different conditions. So you press all the buttons in different combinations. You press multiple buttons at the same time. You don't press any buttons, and you take long, like minutes-long captures to see if you can see patterns, right? So you resort to all of your grep and sort and your bash kung fu is very useful here because there are no tools to automate this so far. For example, like in our case, we noticed that by sorting the packets, sorting the payloads that we've captured using the first byte, we noticed that the first byte was taking specific values over time. So by looking over time at the packets and by sorting them, we will obtain two very similar sequences, and we see that maybe that's a sequential ID. That's sort of a counter, right? And then we started looking at only one of the values. So we select all the packets having the same sequential ID, and we've noticed that the following five, actually four, I'll tell you why four. There's a mistake here in the picture, but the following 4 bytes were all taking the same values. So we said, maybe that sequential ID has something to do with the following bytes as well. But most importantly, we said, oh wait, there's something that reminds me about having a 4 bytes code. And on the label on the back of the device, we remember there was a pairing code which looked like made of 4 bytes, right? Even though it was showed as a numerical alphanumeric string here, it could be a sequence of 4 bytes. So we said, let's take a look at the original captures taken with the original pairing code. And then let's take more captures, but this time we use the USB programmer that was shipped with the device. Yes, you can connect these devices to a computer to customize it, and they sell this as part of the product. So the end users can do this. We set the pairing code to all zeros. So we said maybe we can see through if there is any transformation with the payload. So we started and we started looking, and we tried several logical operations between these two captures until we saw that we could see, using XOR, we could see that the field containing the real pairing code would show into the transformed packet. And the same was for the other packets. I mean, once we figured out how to compare these two captures, we figured out also the other fields. And this is how you usually proceed, and how we proceeded in our work. I want to give a big thank to the developers of Universal Radio Hacker, which we and other researchers have used extensively for our work. This is a great piece of research tool that I really recommend to use to anyone who is into radio frequency security. Great. So after this, I want to go through briefly the white box analysis. So at some point, we figured out most of the details of the radio transmission, but we wanted a confirmation, right? So we wanted to understand more about these systems. If you open up the box, most of the times these systems are made of 1 or 2 MCUs. One MCU is for handling software upgrades, and the other one is the actual main microcontroller. And then you have one radio chip, which is, of course, taking care of the communication. Using a microscope or using a high resolution camera, you can take high resolution pictures. This is a 5mm package. And you have to use also like tangent light if you want to see the prints on the printed digits on the chip, if you want to identify the chip. So we did this, and we identified this specific vendor was using the Texas Instrument ChipCon 1120. Why we did that is because we want to understand how the MCU talks with the radio chip. So in this specific case, it was using a SPI protocol, which is a serial protocol, very common in embedded systems. So if you want to see actually what these two units are talking, you hook up a logical analyzer, and using a logic analyzer software, you can decode the waveforms into a bit stream. Great. So again, like we did with the radio, we are halfway through here. Because if you're lucky, that bit stream is the actual payload, right? In all the radios, the MCU would send directly the bit stream to the radio for transmissions. But in modern radios, this bit stream is only a transport, sort of a physical layer for a more complex protocol on top of that. And the good news is that these protocols are documented. The bad news is that every vendor can do their own, right? So in order to understand the semantic of the protocol on top of any SPI protocol, most of the time it takes a lot of studying of the datasheet to understand this sort of a mini language on top of the SPI, in order to be able to write a small disassembler. This is what we had to do. To give you more abstraction and understand, for example, if the MCU was trying to read or write into the register space, right? What are the exact opcodes? I mean, they're not really opcodes, but allow me this analogy, what are the opcodes that are used to access a register in read or write? Or if the MCU is trying to send a command to the radio to put it in idle or to flush the buffers or whatever. Or if the radio, most importantly, is pushing data onto the FIFO buffers, right? And this is most of the time what the radio is meant to transmit. This is our payload, right? So this was very useful because it allowed us to confirm that what we were sniffing from the radio was actually correct, that we had built an accurate receiver. So at the end of the day, what you have is the entire understanding of the semantic of the protocol. Interestingly enough, in the paper we had promised that we would release this decoder, but during the review window of the DIMVA paper, someone else created a similar decoder for a similar chip, still in the chipcon family. It's not the 1120, it's the 1101, which is still pretty similar. So now, if you want to be able to decode spies from TI, you can just use this kind of tools. So at this point, we have complete knowledge of the protocol. We know everything. We are able to forge commands out of thin air. For the details, please look into the paper, or you can ask Marco, or you can ask myself via email if you have any specific questions. As a bonus, we release RFQuack. Marco, if you have some stickers with you, please make sure that you deliver them to the DIMVA friends. It's a research tool that you can use to do RF analysis with the same simplicity of SDR, but with the performance of a hardware and with much lower price. So you're able to change the radio chips very easily because they are modular, so you can still retain flexibility, but you have the accuracy of hardware demodulation because everything is implemented in hardware, and there is a nice firmware that you can interact with. It's open source hardware, open hardware, open software. So open source, sorry. So you can just use this GitHub repo if you're interested. So why are we doing all of this? Of course, because we want to raise the awareness. As I said at the beginning, there is very little understanding of security in this space. So I think that more researches like this one are needed. My personal gut feeling is that there might be many others legacy radios used in industrial applications that they probably suffer from the same vulnerabilities. So more research in this space is definitely needed. One of the first nice effects of our research came from a recent visit to the Hannover Messe, which is a large industrial exhibition in Germany, where we got approached by a person sitting in a standardization committee working on the international standard for safety of these equipments. And he said that thanks to works like ours, and specifically thanks to our work, he is pushing for modifications in the standard so that not only they take care of safety, but they also take care of security, which is something that is mandatory. So since time is up, I will skip directly to the conclusion, which are very simple. There is no conclusion. I will let the audience send questions to my colleague Marco, who is there, or in the YouTube live channel, which I will keep open if people are interested, or just send us email if you have any other specific questions. For now, I would like to thank all the DIMVA audience to allow me to do this remotely, and I'm really sorry I couldn't be there. Thank you very much.